All right. So we talked about Le Chatelier's principle a lot in 105 and 106. Do you remember Le Chatelier's principle?
I think I do. So let's see. It's like if you alter the equilibrium somehow by removing product, for example, the equilibrium will shift towards the product side.
That's good. That's a good example. Le Chatelier's principle essentially says that if you add reactant or remove product or change, somehow perturb the equilibrium. And now there's multiple ways, because if I have a chemical reaction that is uh, exothermic in nature, right? So for example, here's a chemical reaction, A and B going to C. And if I say that the delta H for this reaction is a negative value, what does that delta H negative mean again?
Oh, that it releases heat?
That's right. Then I can write heat here as kind of a product, right? So Le Chatelier's principle says that if you alter the equilibrium by changing the concentration of one of the reactants or products, or by adding heat even, or removing heat, right, changing the temperature, then you will alter the equilibrium of the reaction. You will alter, the equilibrium will shift to compensate for whatever perturbation you add to it. Okay, so what happens to the solubility of silver chloride if we add HNO3 in this reaction here, 6.54? So here's the equilibrium reaction, and we're going to add HNO3. Well, HNO3 is a strong acid, ammonia is a weak base, and you're going to create ammonium ion and nitrate ion when you react HNO3 with the ammonia. And then the presence of the ammonium ion, right, is going to contribute to adding nitric acid lowers the concentration of ammonia. And if that lowers the concentration of ammonia, then this products over here will have, the silver chloride won't be able to react with the two ammonia here. And so these will react and be able to create more products. So that means the reaction is going to shift towards the left from products to reactants. And thus that will decrease the solubility of the silver chloride, because the left here is the insoluble form of the silver chloride, and to the right you have the soluble form. Okay, very good. Most reactions involve reactions in product dispersed in solvent. If we change the amount of solvent by diluting the solution, then the concentration of all the reactants and products must increase. So Le Chatelier's principle can also be influenced if we lower the amount of solvent. So let's look and see how the change in concentration of everything in our equilibrium statement changes the equilibrium constant. Okay? So, for example, if I call this equilibrium beta, this equilibrium statement here beta, and then I make an alteration, a change with a new quotient here is, here I'm doing multiplying everything by 0.5, so I'm having the concentration, right? Every concentration here is decreased, divided by 2, except for this one here, right? It's going to be 0.5 times 2, right? But then the result is, if we just put in any values here, 1 for all of these values, and compare that to 1 here, the result is going to be 4b, 4 times as much, right? So here I have 4 times as much b as this value here initially. So essentially, when I've changed the concentrations, decreased the concentrations of all of these, that's simply by adding water to the whole thing, for example, then I have increased the equilibrium concentration fourfold. And if the concentration is increased, if this value increases, that means the reaction is going to go towards the right. More product will be present in the equilibrium. Okay, did that make sense?
Kind of. Not quite sure though.
Well, let's look at an example on paper then. So if I have a chemical reaction, any old chemical reaction, A plus B going to C plus D, whoops, D. All right, the equilibrium expression here is CD over AB. And let's give that some value. Let's say that that is X. Is that okay?
Okay.
Now, if all of a sudden I alter the concentration, oops. Let's put a 2 in here, squared. Now, let's say I alter the concentration of everything here by adding water to the whole solution, right? So let's say I've changed the concentration. Actually, let's do the opposite because we already did one of those. Let's change the concentration by doubling all of these, all right? So if all the initial concentrations here were 1, and we would get X, now we would get 2 squared there, 2 and 2. So this would happen when you would kind of get rid of some water, right? Dehydrate the solution. Then how would this now compare to X? If this was X and these were whatever concentrations they were initially, and now I'm doubling them, right? So if this one here, where these were all 1, that would equal 1. This one here would be 2 times 2 is 4 times 2 is 8, right? Divided by 4, so then this would be 2x. So as I double the concentration of these components here, because the 2D over here, right, that's what's driving this process. Before, the 2 was down below, but I've increased the equilibrium constant. Let me get this a little higher here for us. Actually, just pull this up. Another way to think about that is here I have 2 species in equilibrium, and here I have 3 species in equilibrium. And for these 2Ds, right, these 2Ds, to find each other and to find a C, it's more difficult, right? It takes more, it's a lower probability, right? Because 3 things need to find each other. But here, only 2 things need to find each other. So if I increase the concentration of everything, then I improve the likelihood of these 2 things finding each other, whereas these ones here, I've increased the concentration, but it's harder for them to find each other. Now let's do the same thing with a different chemical reaction, more simple one, just A reacting to B, okay? If A, concentration of B over the concentration of A, right, that's our equilibrium statement, equals X, right? And then I change the concentration to, let's say, 2B or 2A. Now, I'm not actually, yeah, that's it right there. Then my X is going to be, whoops, it's going to be the same, right? It's going to be the same. So when you don't have a difference in the number of molecules on either side, increasing or decreasing the concentration of those compounds, reactants and products, won't change the X there, right? Because we have 2 2's there. Okay, good.